Hello, welcome to your week 5 lecture video. This week we're going to look at two chapters, 6 and 7, which are the data link layer and Ethernet switching respectively. So without further ado, let's dive into chapter 6. Here's everything you're going to be able to do by the end of this. So the data link layer, which is layer 2 of the OSI model, is responsible for communication between end devices, specifically their network interface cards on the end devices, right? Without a NIC, you can't do anything. The data link layer allows the upper layer protocols to access the physical layer media and encapsulate the layer 3 packets, which are your IPv4 and IPv6. We're going to be looking at that next week. Actually, I think we're going to be looking at the next set of slides. Into your layer 2 frames. So layer 3 we're dealing with packets, layer 2 we're dealing with frames. Layer 2 also performs your error detection and rejects corrupt frames as needed. So you see we've got our layer 3 packet. It's encapsulated within a layer 2 frame. There's a variety of standards that we use at the data link layer, and they're specific to the type of network that you're using. Ethernet, wireless LAN, wireless personal area network, etc., right? And we actually logically divide the data link layer into two sub-layers. The LLC, or logical link control, and the MAC, the media access control sub-layers. Two sub-layers of the data link layer. So the LLC, that's the sub-layer of the data link layer that's responsible for communicating between your networking software at the upper layers and the device hardware at the lower layers. The MAC sub-layer is purely responsible for encapsulation and controlling access to the media. So at the LLC sub-layer, we're going to see 802.2. It's an IEEE standard. Anytime you see 802 dot something, you know it's an IEEE standard. And in the MAC sublayer, we could have Ethernet, which is 802.3, for fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet, so on and so forth. Any Ethernet standard is 802.3. Wireless standards are always 802.11. Usually you see a 1 or 2 letter revision behind it. If you're buying a wireless NIC or a router, it might be 802.11ac or AX compliant, AX being the most recent one. Or IEEE wireless personal area Bluetooth and RFID is 802.15. It's an IEEE standard as well. Again, anytime you see that 802 number, you know it's an IEEE standard. So packets exchanged over a network might experience a number of data link layer and media transitions. Every hop along the path, at every hop along the path, a router will perform 4 basic functions all at layer 2. It'll accept the frame from the network medium, because they can't do anything until it accepts it, right? It'll de-encapsulate the frame and look at the encapsulated packet. It will then re-encapsulate that packet with a new frame and forward it out the appropriate interface onto the next network segment so it can continue its journey. There's 4 organizations that define standards we deal with at the data link layer. The IEEE, the Institute for Electrical and Electronic Engineers, and I can never remember, I always mess that one up, there's too many E's in that one. The ITU, the International Telecommunications Union, the ISO, the International Organizations for Standardization, and ANSI, the American National Standard Institute. Now, when we look at network topologies, which is going to be an important thing that you're going to start, well, you've already been looking at them, right? You've been looking at diagrams in your book. That's all the topology is. It's a network diagram. So when you've been cabling things up in the lab, that's a little topology. Maybe small, but it's a topology. You tend to see larger ones that describe the entire network, though. And there's two types of topologies that we use: the physical topology and the logical topology. The physical topology shows the physical connections and how the devices are actually interconnected. The logical topology will include things like IP addressing and virtual connections between devices using interfaces. Hopefully that makes sense so far. Again, I would pause and ask, but I can't because we're online and it's asynchronous. There's three types of physical wide area network or WAN topologies. Point-to-point, which is the simplest and most common WAN topology. It's just a single permanent link between two endpoints, hence point-to-point. Hub and spoke, which is, it's like a star topology, but there's a central site that connects all the branches through individual point-to-point links. And then mesh. With a mesh topology, every site is connected to every other site. It's great because it gives you high availability and higher bandwidth and removes any chance of a single point of failure. But it's pretty expensive and complicated to configure because every device needs to be connected to every other device. So here's what they look like. So here we see we've got a physical point-to-point topology. So we've got one node here, another node here. They're both connected. Now they might not share media with other hosts, and because all of the frames on the media can only travel from, or rather between, two nodes, right, from one source to one destination in either direction, then the protocols for this are very, very simple because the topology is very simple, right? It's just a line. Now, end devices in a LAN are usually interconnected using either a star or extended star topology. You'll have a variety of PCs that are connected, or laptops are wireless too, right? But PCs that are actually physically connected through a switch. Now, star and extended star topologies, the reason they're so common is because they're very easy to install, they scale well, they're pretty easy to troubleshoot. But earlier topologies, like early Ethernet and Token Ring, which is a legacy protocol, gave us two additional topologies, which nobody uses anymore. Or, I shouldn't say nobody uses, but really nobody should be using anymore. If there's anyone using this, it's really old, obsolete technology, right? It's possible that there's people out there using this, but hopefully not. Hopefully never encounter these. Bus. With a bus topology, all the devices are chained together and terminated on either end. So packets have to traverse from front to back, right? One end to the other, and it's very slow. Lots of single points of failure too, right? If one PC's off, the whole thing's down. With a ring or token ring topology, each end system is connected to its neighbors in a ring. And there's a token that's passed, and each device can only send data if it has the token, hence the name token ring. Nobody uses that anymore, but we did at one point in time. Now, on a topology, on a network, devices can work in either half-duplex or full duplex communication. With half-duplex, it's a bit slower, because only one device can send or receive at a time, and the medium shared, right? The medium shared with everything. It's really only used nowadays in wireless. You see half duplex and wireless. It's one of the reasons why it's so slow, or rather slower than a wired connection. And if you've got a legacy bus topology with a hub, which hopefully you don't see, but if you see anybody with a hub, convince them to replace it with a switch because they're better. But that's where you might see half duplex communication. Full duplex communication is a lot better. It allows both devices to simultaneously send and transmit, so nobody has to wait. You just send and it's good, and you can receive at the same time. All switches operate in full duplex mode. So it's a good reason to have switches in your topology, isn't it? So with anything using half duplex, you have to have some sort of mechanism to determine and inform the other devices who's allowed to communicate and who's not, right? So we used to use CSMA CD, carrier sense multiple access with collision detection. We still use CSMA CA, carrier sense multiple action with collision avoidance instead of detection. CSMA CA is used in wireless LANs. CSMA CD used to be used on bus topologies, which is legacy. You shouldn't see these, right? But in either of these topologies, there has to be some sort of control or controlled access with the legacy ones. So to determine who can send data and for how long on the medium. It's used on things like Token Ring and ArcNet, which again, you shouldn't see. CSMA CD used on legacy Ethernet LANs and wireless. Sorry, wireless is CA. Ignore what I said about wireless. Wireless is CSMA CA. So it operates in half duplex. Only one device sends, the other receives at a time. And it uses collision detection to govern when a device can send and what happens if multiple devices send at the same time and you get a collision. If a collision is detected, all the transmitting devices will simultaneously well, they're sending data at the same time, right? And it's going to collide, it's going to cause a problem. So the devices detect that collision, and then they stop sending data, and they wait a random period of time to retransmit data, and hopefully they don't choose the same random period of time, or else there's another collision. But generally speaking, not an issue, right? And it would just recycle the process if they did. CSMA CA, that's the one you're going to see. So it's used in wireless in 802.11. Look at that, IEEE 802.11. What did I say? So this operates in half duplex. So again, only half duplex, only one device can send or receive at a time. And it uses collision avoidance to do the same thing, right? When transmitting, devices include a time duration for the amount of time needed for the transmission. And the other devices receive that information, and they know how long it's going to be unavailable, so they're just not going to send anything. Which is a good thing, right? You don't get collisions that way. They're avoided, hence collision avoidance. Hopefully that makes sense so far. It's going to be a quick one. Now, when we're looking at an actual data link frame, this is the data inside, right? It's encapsulated by a data link layer header with a footer, a trailer for the footer. Sorry, data link layer. Stumbled over my wording. Header and trailer that forms a frame. So the frame has three parts: the header, the data, and the trailer. The header and the trailer vary according to what protocol you're using, and the amount of control information that's contained within these depends on what protocols you're using. But you tend to see things like the frame start. That makes sense. It identifies the beginning and end of a frame. There's a frame stop, right, for the end. The addressing, so that's going to be your MAC addressing, right, because we're dealing with the data link layer, so that's layer 2 MAC addressing or physical addressing, layer 2 addressing. All of those things you're going to hear, all those terms you're going to hear. The type, so the type is used to identify what layer 3 protocol is encapsulated. Control indicates if there's any flow control services and what they are. The actual data is the payload. And then the error detection, which goes in the trailer, it's used for determining issues in transmission, so the frame can be checked and dropped if needed. So layer 2 addresses, or MAC addresses, or physical addresses, they're all the same thing. They're contained in the frame header, and they're only used for the local delivery on a single link. And every single device that receives that frame examines the frame, the existing one, when it receives it, to determine the source and destination, strips it off, looks at the packet, and re-encapsulates the frame with its own new header, with itself as the source, and the next hop in the journey as the destination, and forwards it along the way. So, in conclusion, we're looking at we talked about logical topologies and physical topologies, right? And a variety of different data link protocols. So the physical media will determine what protocol you're using. If it's Ethernet, right, it's going to be Ethernet. If it's 802.11, it's wireless. You could also be using things like point-to-point, PPP, HDLC, which is default on Cisco devices, I believe, high-level data link control, and frame relay, which is really old and you're not going to learn anything about really in this course. Every single one of these protocols performs its MAC, its media access control abilities differently for the specified topology. So things to take away from this chapter. Full duplex and half duplex, right? With full duplex, both sides can communicate at the same time. They can send and receive. With half duplex, only one side can send. The other has to wait until the former is done sending so it can receive. Hopefully that made sense. If you have any questions, of course, bring them to the lab. And with that, we're going to move on to Ethernet switching. So now we're dealing with, we're still at layer 2. I think we're doing layer 3 next week. So we're going to look more in depth at frames and the sublayers, MAC addresses, MAC address table, and different switch speeds and forwarding methods. So we're dealing with frames, right? So we're dealing with the physical layer and the data link layer, right? Frames are layer 2, but Ethernet operates at both. And it's a variety of different technologies that are defined by the IEEE in their standards 802.2 and 802.3. So the 802 standards, including Ethernet, use 2 sublayers to operate. The LLC, which is 802.2, that places information in the frame to identify which network layer protocol is being used. And then MAC, so that's 802.3 if you're using, should be 2. They have that backwards. Something's messed up on that slide. It should be 802.2. Pretty sure. Either way, if you're using Ethernet, 802.11 for wireless, 802.15 for wireless personal area networks, which we just looked at these, right? So this is responsible for data encapsulation, media access control, and providing your data link layer addressing, or layer 2 addressing, which we just talked about in the previous lecture. So that should be pretty fresh in your mind because we're not even 20 minutes in yet. So the MAC sublayer, that's responsible for encapsulating the data and accessing the media. The data encapsulation includes 3 things. The frame, so that's the internal structure of the Ethernet frame. Your addressing, so this is the source and destination MAC address that ensures that the frame will be delivered from one NIC to another NIC on the same LAN. And your error detection. So this is a frame check sequence. It goes in the trailer. It's used to check the frame, make sure it hasn't been corrupted, and if it has, appropriate actions will be taken, i.e. it'll be dropped. The 802.3 sublayer includes specifications for different Ethernet communications over different types of media, such as fiber and copper and wireless. Legacy Ethernet using bus topology or hub is half duplex. Ethernet is half duplex if you're using wireless, and if you're using modern switches, they all operate in full duplex, which is great because full duplex communication and just having a switch eliminates collisions, so you don't need CSMA CD at all. Now, frames have a minimum and maximum size. The minimum size is 64 bytes. Maximum size is 1518 bytes. And the preamble is not included in this calculation. Any frame less than 64 bytes is considered a runt frame or a fragment from a collision, and it's automatically discarded. Anything bigger than 1500 bytes are jumbo frames or baby giant frames, and they will also be dropped unless your equipment supports it. So if that size is smaller than the minimum or greater than the maximum, the receiving device just drops it. The only time you're going to see a jumbo frame accepted is if you're using fast Ethernet or gigabit Ethernet, and your configuration supports it. Now, MAC addresses. Useful to know. They're a 48-bit binary value. They're 12 hexadecimal values. And we learned about hexadecimal last week, right? We did some conversions. So we have 8 bits, which is 1 byte. It's a common binary grouping, right? We assume the lead, or we don't assume, we include the leading zeros to complete that full 8-bit representation where we're looking at the binary version of hexadecimal. We tend to represent these with a 0x in front of them, so we can determine whether it's an actual hexadecimal number. Though you might also see a subscript 16 or just an uppercase H at the end of the number indicating it's hex as well. Those are other conventions. It doesn't have to be the 0x. Now, every device on a network has a MAC address, and every MAC address has to be unique. And because they have to be unique, we have to have ways of making sure they are going to be unique. So every single vendor that sells networking equipment has to register with the IEEE and obtain a 6 hexadecimal code called the OUI, the Organizationally Unique Identifier. So this is 6 hex values. It's the first half of the MAC address. The back half of that MAC address, the vendor can do whatever they want with as far as assigning those. So this generally guarantees that you're going to get unique MAC addresses throughout. There's a very small chance if you happen to buy 2 pieces of networking equipment from the same vendor, like 20 years apart, then you might very, like 0.0002% chance that you're going to get the same MAC address, but highly unlikely. Right? Very, very small. So when devices forward a message over an Ethernet network, the header includes a source and destination MAC address. The NIC receives that frame. It'll look at the MAC address to see if it matches a physical one that's stored in RAM. If there's no match, it discards the frame. If there is a match, then it passes that frame up the OSI layer. The packet is de-encapsulated, and they figure out what to do with it next, right? Now, a note on this. NICs will also accept frames. There's a broadcast and multicast MAC address, so they'll accept those frames as well. Now, any device that is the source or destination of a frame will have a NIC, so it has to have a MAC address. This means workstations, servers, printers, mobile devices, routers. Every piece of networking equipment has a MAC address. There's a couple special ones, a couple types of MAC addresses. Unicast, so these are unique addresses that can be sent to one place, right? One destination, one device, unicast. The process that devices use to look up MAC addresses associated with IP addresses, that's ARP. It's Address Resolution Protocol. Also in IPv6, it's used in neighbor discovery, the neighbor discovery protocol. Now, Ethernet frames could be broadcast as well, aside from unicast. They can also be multicast, which we're going to look at in a minute. Broadcast Ethernet frames will have a destination MAC address of all Fs, 48 ones in binary. These frames are flooded out every single switch port except for the switch port it came in on. And they will not be forwarded by a router, or dropped by a router. If the encapsulated data is an IPv4 broadcast, that means that that's going to be broadcast to all hosts on the same network as well. Again, the router will not forward it out the other side. For now, anyway. There's exceptions to this we'll talk about later, but so far as you're concerned, it's not going to happen. Next up, we have multicast addresses. So these have destination MAC addresses of, well, those values there. If it's IPv4, or the other value there if it's IPv6. There are reserved multicast addresses for encapsulated data which isn't IP, such as spanning tree, which we're going to look at later in the semester. And multicast MAC addresses are flooded out all switch ports except for the incoming port, unless the switch is configured for multicast snooping. These also won't get forwarded by a router unless you configure the router to route multicast packets, which you could do. Now, because these are represented as a group of addresses, they're usually called, or sometimes called a host group. They can be used as the destination as well, but the source will always be multicast if that's the case. And just like unicast and broadcast addresses, multicast IP addresses are required as well. So you have to have a multicast IP and a multicast MAC address if you're using something that multicasts. I, again, would normally pause and ask if that makes sense so far. I hope it does. We're flying through these. Now we're going to look at the MAC address table. So this is any layer 2 Ethernet switch has a MAC address, or uses MAC addresses at layer 2 to make forwarding decisions. It doesn't know about the other protocol that's being carried in the packet, and it doesn't care. It just makes decisions based on its MAC addressing table. So to build this, a switch will examine its MAC address table every time it receives a frame. And it'll make a forwarding decision based on what's in there. And if it doesn't know where to send it, it'll be broadcast out every single port except for the one it comes in on. When a switch is turned on, the MAC address table is empty. And a note about these are sometimes referred to as CAM tables, Content Addressable Memory Tables. So you might see those terms used interchangeably. Every single frame that enters a switch will be checked for new information. The switch will look at the source MAC address in the frame and the port number that it was received on, and if the MAC address isn't in its table already, it gets added to the table with the incoming port number. If the address does exist, the switch will update the refresh timer for that entry so it stays in the table longer. By default, switches keep an entry in the table, for the most part, for 5 minutes. It's also possible that the address might be in the table but on a different port, the switch will treat that as a new entry, and that new entry will replace the other one with the current port number. This happens if you disconnect an Ethernet cable and connect it into another port, because you might do that, right? Maybe you connected it to the wrong one. So if the destination MAC address is unicast, the switch looks for a match in its table to determine where to send it. If it finds a match, it forwards it out that port. If it doesn't find a match, it forwards it out every single port except for the one it came in on, the ingress port. This is known as, or called, I was going to say known, but unknown is in the description. This is called an unknown unicast. Now, if that destination MAC address is broadcast or multicast, the same thing happens, right? The frame will be sent out every single port except for the one it came in on. Now, as switches receive frames from different devices, it populates its MAC address table, and by looking at those frames each time, it looks at the source and updates its table. And it uses this information to filter out frames through the various ports. Hopefully that makes sense. Now there's two methods you can use on Cisco switches to forward frames. This is a good test question. Store and forward and cut through. With store and forward switching, the frame will receive the entire frame, compute its CRC to determine that it's not a corrupt frame, and forward it out the correct port. If the frame doesn't pass that CRC checksum, it's of course dropped. With cut-through switching, you get the switch forwards the frame before it's completely received. It has to receive at least the destination address of the frame so it can figure out where to send it. So the big thing between the two of them, the advantage of store and forward, is that it determines if the frame has errors before it propagates it. So if it has an error, it's going to drop it, and those aren't going to be bouncing around your network consuming additional bandwidth. Store and forward switching is required if you're going to implement quality of service, QoS. And any time where you want to classify traffic for priority, right? So for VoIP, right? VoIP has to have a higher priority over anything else. So you're going to have to use store and forward. You can't use cut through if you've got VoIP. Cut through is faster. That's why you might want to use this, right? It's a lot faster. But the switch will start sending the data out as soon as it's received, even if the transmission is not complete. It buffers just enough of the frame to read the destination MAC address, so it can figure out what port it needs to go out, because it still has to go through that MAC address port lookup process. And the switch doesn't perform any error checking at all on the frame. There's two variants of this, fast forward and fragment free. Fast forward switching gives you your lowest level of latency. It just starts forwarding the switch as soon as it reads the destination address. But this might result in errors being propagated out your network. Fragment free it's faster than store and forward. It's somewhere in the middle, right? It's a bit slower than fast forward switching. So it actually does an error check on the first 64 bytes, because that's where most of the errors and collisions occur, within those first 64 bytes. So if the first 64 bytes are good, then it'll forward it along. A little bit slower, but not so bad. Now, switches can use a variety, we've mentioned buffering, right? They can use a variety of techniques to buffer or store those frames before forwarding them, because ports get busy, right? You can use a port-based memory or shared memory. With a port-based memory, there's queues where the frames are stored that are linked to specific incoming and outgoing, or ingress and egress ports. Frames are transmitted out the outgoing port only when all the frames ahead in the queue have been successfully transmitted. Think of it as like a line, right? It's possible for a single frame to delay all the frames in memory because of a single port. And this delay occurs even if the other frames could have been transmitted because those ports are open. With shared memory, all the frames are deposited into a common memory buffer that's shared by all the ports on the switch. And the amount of memory in the buffer is dynamically allocated based on how busy the port is. Frames in the buffer are dynamically linked to the destination port, which gives you a faster transition from one port to another without moving to a different queue. Shared memory gives you larger frames that can be transmitted with fewer dropped frames. If you're going to use asymmetric switching, where you've got a higher bandwidth connection on one side of the connection than the other, then you're going to likely use the shared memory, right? Because you can have more bandwidth dedicated to certain ports. Now we've mentioned duplex. We haven't talked about speed though. These are two of the most common basic settings that you can use on a switch. The two duplexes you're going to see are half duplex and full duplex, which we talked about previously. With full duplex, both ends of the connection can send and receive data at the same time. With half duplex, only one end of the connection can send at a time. You may have most Ethernet switches auto-negotiate this. So once the device is plugged in, it will auto-negotiate to determine whether it should be operating in full or half duplex. A note though, gigabit Ethernet ports only operate in full duplex, and really, you're probably going to see full duplex more often than not. Duplex mismatch is one of the most common causes of issues on Ethernet links, and it occurs when one port's configured to set in half duplex and one port is configured to set in work in full duplex. Like I said, configured to set. When one end is set to work in half duplex and the other end is set to work in full duplex. This could happen because either both ports or both links have been reset and the auto negotiation didn't work for some reason. It could also happen if you've not used auto negotiation and you've manually configured it. I tend to just leave the auto negotiation, but they actually recommend you just set them as full duplex manually. Auto negotiation should take care of it in my experience. But what do I know? I'm not going to argue with the Cisco slides. We're just about done, 40 minutes in. Auto MDIX is an awesome thing. When we talked about cabling previously, right? When we talked about cabling, we talked about types of cables. We talked about straight through and crossover cables, and I mentioned that you used to have to remember types of devices when cabling things up. Auto MDIX is an awesome feature that allows us to not have to worry about that. So you can use any type of cable, and the router and switch or whatever will figure it out. So if you put in a crossover cable when you really needed a straight through, it'll just figure it out through Auto MDIX, and it will work anyway. So when this is enabled, it doesn't matter what cables you put on what ports, it's going to work. Straight through and crossover, I'm not talking about rollover at all, right? It's enabled on by default on newer versions of iOS, 12.2 or later. You could disable this if you want, so you should always use the correct table type and not rely on this, but I mean, it's going to be there, and if it's disabled, you can just re-enable it. You just use the command MDIX auto. So what did we learn? Oddly, the last slides didn't have a what did we learn thing at the end. We talked about data link and physical layer and how Ethernet is a protocol that operates at both of those, right? We talked about the LLC and MAC sublayers. We looked at Ethernet frames. We looked at MAC addressing. So MAC addressing is a 48-bit value that's expressed as 12 hexadecimal digits, which is 6 bytes. When a device forwards a message on the Ethernet, the header includes the source and destination MAC address, and these are going to be different than the ones we look at in lower layers or upper layers. We looked at MAC address tables or CAM tables, so switches examine each frame to learn new information and match that frame against its MAC address table to determine where it should be sent. If there's no match, then it's broadcast out every port except for the one it came in on. We talked about store and forward and cut-through switching. Store and forward is a bit slower, but it runs an error checking, a CRC. Cut-through is faster, but you lose that, right? And cut-through has 2 variants, fast forward and fragment free. We talked about memory buffering, and we talked about duplex settings. Full duplex, both sides can communicate at the same time, send and receive. Half duplex, only one side can send or receive at a time. And that brings us to the end of our lecture. So take care, be safe. I'll see you in this week's lab. Bye for now.